Hello and welcome to this Bentley Success Factors webinar on reverse engineering in MAXSURF by Dr. Pat Couser. In this webinar we will be looking at modelling methods and tools for reverse engineering existing vessels to create digital models in MAXSURF, which can then be used for analysis or used as parent designs for new vessels. We shall briefly review what we mean by reverse engineering in this context. Then we shall look at some typical sources of data which could be available as a basis for generating a digital vessel model in MAXSURF. Finally, we shall look at some specific workflows in MAXSURF and the modelling tools that are available to help you create your digital vessel models. In part 1 of this webinar we will focus on the workflow for creating tri-mesh models in MAXSURF. These are particularly useful when hydrostatic or hydrodynamic analysis of existing vessels is required. In part 2 of the webinar, we will look at creating NURBS surface models in MAXSURF. The classic definition of reverse engineering is the analysis or study of a device in order to learn the details of its design, construction and operation, perhaps to produce a copy or an improved version. So looking at a CAD modelling example, we take the real object, measure it, and then create a numerical CAD model of the object from those measurements. In this presentation we define reverse engineering as taking some raw geometry data, which may be from an existing vessel. This could be a CAD drawing, numerical offset data, photos, line plan, etc. If necessary, measuring the object and organising the measurement data, then creating a numerical surface model in MAXSURF. There are many reasons why we might want to do this. These include generating a numerical model of the as-built vessel, creating a model for reanalysis of vessel performance if an existing model is not available. This is often required after a refit where there may have been a change of mass or change of centre of gravity, and a new stability book or reassessment of operational envelope is required. Conservation of vessels of historical interest in digital form, for example in a museum, or generating a basis hull form with the aim of future modification to improve the design. Surface fitting to existing data is one of the harder aspects of using MAXSURF, or any NURBS modelling software for that matter. Unlike in chess, humans still retain an edge over computers in this domain. MAXSURF provides many useful tools and can speed up many aspects of this task, but there is no single methodology which can be applied to all scenarios. This is not the first thing you should be attempting in MAXSURF. You should first gain some experience in modelling techniques and how to use the software before attempting surface fitting. Look at the numerous samples that are shipped with MAXSURF. Experiment with the ways of modelling specific vessel features, transom sterns, chines, spray rails, etc. Modify existing models and get to know the software. So before attempting to recreate a digital model of an existing design, you should have a clear idea of how to go about modelling the vessel type in question, and how best to achieve the important and relevant design features. Before you start, you should have a clear idea of surface layout and topology, where to use surface trimming and where to use surface bonding, and the simplest way to achieve the desired vessel model. Remember that the measured data from the original geometry are just an additional guide to help you obtain the required hull form. What is required by MAXSURF? I've included this section as a reminder of what is required if we want to generate a model that can be successfully used in the MAXSURF system for analysis. These constraints are the same irrespective of whether we are modelling an existing vessel or creating a new vessel from scratch. The principal requirement is that at any cross-section the model must satisfy the following constraints, and this is so as to be able to intersect with the water plane to calculate the section hydrostatics. You're allowed multiple closed contours, or at most one contour may have a single opening, and this single opening will be closed with a straight line. You're not allowed any self-intersecting contours, or any contours which intersect another contour. Neither are you allowed contours that are wholly contained within another contour, and yet finally you're not allowed any unclosed line segments. And here we have a few examples. So starting from the left we have a rib, and you can see the two buoyancy chambers on the side, which are completely closed contours. The main hull is open at the top and would be closed with a straight line for the deck. Then we have a catamaran sample, and this is formed by one completely closed contour. On the right we have an example of an aft sloping transom, and why we need to include a transom surface to give the upper and lower closure of those contours. if we didn't have a transom surface, we'd just have those two contour lines, and the software wouldn't know to close along the top or bottom to form a monohull, or to close each contour independently to form a sort of catamaran. In these examples we can see a container ship with a bulbous bow, and again we have one completely closed contour and another contour which is open, which will be closed with a straight line. The middle one shows an example of a yacht where we have completely closed contours, including the deck and coach house, and a part of the section through the keel and the keel bulb. And the final example shows some tricks we can use to model, for example, a semi-submersible, and here we've included very small gaps where the bottom horizontal strut joins and where the diagonal struts join the deck. There are very small gaps, which means it's one single contour that doesn't intersect itself. So within MAXSURF we have two model types. First is a tri-mesh model, where the measured data points are connected to form a triangular mesh. This implies linear interpolation between the mesh nodes. It is suitable for all hydrostatic and hydrodynamic analyses in MAXSURF. It is generally quicker to generate than fitting NURBS surfaces to the data, but is more difficult to modify and is not smooth. The second is a NURBS surface model. The surface shape can be precisely evaluated anywhere. Again, it's suitable for all hydrostatic and hydrodynamic analyses in MAXSURF. It is easy to modify using, for example, the parametric transformation tool. It is smooth and suitable for production, i.e. plate forming and tracing the paths of stiffeners that are required to follow the whole surface. However, it is generally more time consuming to fit the NURBS to the point data. MAXSURF does not currently have the possibility of a hybrid NURBS and tri-mesh model for modelling the buoyant hull, but NURBS surfaces can be added to a tri-mesh model when they are required to model complex tank geometries. The format of the available input data that defines the geometry to be modelled and the type of MAXSURF model which is required will have considerable impact on the optimum workflow. In this section we should look at some of the common sources of input data and then review the level of difficulty to obtain a tri-mesh or NURBS based model in MAXSURF. We can have unstructured discrete data in the form of a point cloud, typically from a laser scan or possibly manually digitized lines plan, although in this second case the data would normally be structured and ordered along known contours. Both are potentially subject to error, and typical datasets cover a very broad range of data density. The available data for a complete model may be a few hundred or less points in the case of a manually digitized lines plan, or up to tens of millions of points as a result of laser scanning, as seen in this example point cloud from a laser scanned sailing yacht hull. So part of the fitting process will include some form of data reduction and smoothing, i.e. our objective won't be to generate a model that exactly matches all the data points. Structured discrete data, for example coming from another CAD or modelling system, these contain data that are known to be on the exact surface of the vessel to be modelled, i.e. they are not subject to error. These data may be organised on known curves through the vessel, such as sections, buttocks, waterlines and surface edges and features. All these data sometimes come from in a structured mesh, which may have originally been generated for CFD or FE analysis. Finally, we have basis data defined using smooth curves or surfaces. These may be boundary curves or NURBS surfaces which can be imported from IGES, MicroStation or Rhino files, and these may vary from a small number of large surfaces to a patchwork of a large number of small surfaces. There are also a number of less commonly encountered surface types which, though smooth, are not NURBS, for example subdivision surfaces and B-rep surfaces. So as mentioned earlier, the workflow and ease with which a model can be generated depends on the basis data and the desired model type. In this table, the first column shows 5 rows, each with a different type of basis data. Then in the second and third columns, I've shown the relative ease of creating a tri-mesh model and a NURBS surface model in MAXSURF. So in the first row, if we have a high density unstructured point cloud, which also contains error, for example from a laser scan, then it's actually quite difficult to generate a tri-mesh model because we need to apply data reduction and smoothing, and then structure the data to form a surface mesh. for example using some sort of shrink wrapping algorithm. On the other hand, to generate a NURBS surface model, it's not so hard, because we can use the NURBS surfaces to smooth through the data cloud using the built-in fitting tools. However, for some really large datasets, some pre-processing will be required, because MAXSURF can only currently handle point clouds of up to 64,000 elements. The second row is for low-density structured points, but with the possibility of some error, for example coming from a manually digitized scanned lines plan. Generating a tri-mesh can be quite easy because the points are already structured. However, it's not possible to smooth out the data without manually editing the data points, and again fitting a NURBS model is about the same difficulty as with the high-density point cloud. In the third row we have a low-density structured points without error, which may come from CAD drawings. And this is the ideal situation for generating a tri-mesh because there is no need for smoothing, provided of course that the data can be organised onto sections and may be a stem and stern profile curves. If the data format is already in a supported mesh format, then this can be read in directly and requires no further work to produce a tri-mesh. And in this case, generating a NURBS surface is about the same difficulty as with the previous cases. If we have NURBS curves, then the difficulty of generating tri-mesh depends really on what the curves represent. If we have a series of sections and maybe a stem and stern profile, then it will be quite straightforward to generate points from these curves and then generate a tri-mesh. On the other hand, if the curves represent surface edges, then generating a tri-mesh will be much more difficult. There are a number of tools available for generating NURBS surfaces from NURBS curves, including skinning a surface through a set of section curves, as well as creating surfaces from a set of 4 boundary curves. Finally, if we import NURBS surfaces directly, then there's really no point in generating a tri-mesh model. Creating a MAXSURF NURBS surface model is relatively straightforward. However, there may be issues with surface trimming and also the number of surfaces in the model. It may be appropriate to remove some of those surfaces depending on what level of detail is in the imported model. In this section we will look at how you can make use of existing geometry. In particular, we will look at how MAXSURF markers can be generated. Markers can then be used to create both tri-mesh and NURBS surface models in MAXSURF, so the workflow and tools shown are often useful irrespective of the type of model desired. In this first example I shall show you how to digitize markers from a scanned-in lines plan. We'll look at the different background images in each view. The body plan background image is probably the most useful, but the stem and stern profiles are also helpful. First of all, you need to prepare the background image in a graphical editor, rotating it and checking that the vertical and horizontal scales are the same, and also ensuring that the reference point is visible. We'll then define the grid, defining the station locations, waterlines and buttocks, allowing a spare station for the stem and stern profiles. We can also specify where the split location is for splitting the left and right hand side of the body plan view. We'll then go through digitizing the stations and try and add points at each waterline and each buttock on each station, which then makes it easier when you're looking in the other views to check the waterlines and buttocks go through the points. And if they're available, we'll add the bow and stern profiles. There's an option to connect the marker stations with a straight line, and this makes it easier to determine which markers are on the same station. There's also a couple of other tools like being able to edit the last marker and any subsequent markers carry over the data from that previous marker. This can be handy when you're adding points on buttocks or waterlines in the profile or the plan view. You can add one marker, edit the height, say in the plan view for the waterline, and then all the subsequent markers will be at that height. It's also useful if you've got a complex model to use surfaces to group markers, and the surfaces can be hidden and then all the markers that are associated with that surface are also hidden. So here I'm editing the images in an image editor. I've rotated the images to ensure the baseline is horizontal, and I've actually added the 0 point in the profile view to a point that I can click on. And here's the body plan view drawing. I've actually left both the profile and the plan in the same drawing to use in that view. So if I go to the view I want to import the image into and select the image drawing. So the first thing I need to do is locate the 0 point on the image. It's best to zoom in quite a lot here, and from the display menu I can set the background, the 0 point, and just click on the location where the 0 point should be. The image may move off, so if I go to the home view I can now see the 0 point is at the correct location on the background image. I now need to set a reference length, which is going to be the 8th waterline, so I can set that reference length. And I've already set up the locations in a spreadsheet, so I can just copy that data from the spreadsheet. They're actually at 200mm intervals, so that's at 1.4 meters. And that's a vertical distance, positive up. So now my background image is correctly scaled. So I can add the design grid for the waterlines and buttocks and just verify that everything's as it should be. So I've got 6 buttocks and they're at 200mm spacing, but I'm just going to copy that from the, they're at 200mm spacing starting from 0, at 200mm spacing starting from 200. Now I can add the waterlines, and again they're 200mm spacing, but I've already got these data prepared in a spreadsheet, so I can just copy the data from there. So just select that data, copy, and move back here and just paste into here. And I can do the same for the for the buttock names. So here I've got my body plan set up correctly. You can see the stations, you can see the buttocks and waterlines match correctly. There may be a bit of error due to scanning or warping of the paper, but we have to go with the best we can. Now I can switch to the profile view and pick up the data from there. So I'm going to add the other image that's got the profile and the water plane. So again, set the 0 point. So I'm using that point that I've generated in the drawing program. Again, click on that, go to the home view. I can see the image has moved to the 0 point of the drawing. And I'm going to use the 21st station as my reference length. And again, I can copy that data from the spreadsheet I prepared. Remembering that aft is negative because it's behind the 0 point. So now I can set up my station locations in the design grid. So the data menu, design grid. So I'm going to add actually 24 stations, which give me the 21 proper stations plus some placeholders to put the stem and stern markers to group them together. It doesn't really matter what location you give for these, but the fact that you've got an entry means that you can group the markers together for those curves. So we can see here the stations fit pretty much onto the drawing. So just speeding up here again, just going to do the same thing for the plan view. It's the same drawing. Select the 0 point and then specify the reference length. So now I've got my 3 views with my 3 drawings in, profile and the body plan view. And as always, it's a good idea to save your drawing or your design just in case something happens. So now I'm ready to start digitizing the points in the body plan. I'm going to select the station I want to start adding points on with the inset box. So the first one's the stem, I want the second one, which is station 0, and now I can start adding points. So go to the add markers toolbar, and once I've added one I can just press the enter key to enter the subsequent ones. And I'm adding them on the water lines, so that when I go to the plan view I can see the markers in the correct locations for the water lines. And I'm going to turn on the connect marker stations, which will draw a line through those points that are joined together on that station to make it easier to see them. Can now move on to the next section, remembering to change the selected station to station 1. And again, I just have to click on the toolbar to start with, and then I can press enter for the second and extra points. So it's basically just a question of doing that for each of the sections, adding points as necessary. Then moving on to station 2, you can see that at the bottom of the screen there. And again, start with the toolbar and then press the enter key to add extra points. You notice I'm adding them on the buttocks as well as the water lines, and again that's so if I go to the profile view I can check my markers match the buttock lines. So there is a slight error, well not error, but I might want to add an extra marker, so I've changed back to station 1. And it'll automatically do a search to try and work out the best place to insert the markers. So normally the marker order should be correctly adjusted. So here I've almost finished this side, and what we're going to do is set the offset to 0 for these markers, so I can select those markers and press and give the offset, or just select a single marker and give that on the offset. And it's worth checking that they're all exactly on the water line, centre line. Now you notice here I've got station 11 and then station 12 is on the other side. So by selecting station 11 as the split station, it's where when I'm looking in the half view, the forward stations are on the right hand side and the aft stations are on the left hand side, and the split station defines which station is the last station to be drawn on the right hand side. So this is quite helpful when I'm adding the extra points, because it will take into account the offset. So even though I'm clicking on this port side of the vessel, it will give me a positive offset, and that will ensure all my markers are actually on the starboard side of the vessel. So I can just go through as I did on the other side, or for the other sections, adding the points on the water lines and buttocks and any intermediate points we want. So we are just finishing off the transom, and we can check that the points lie on the buttocks in the profile view and on the water line in the plan view. And so now it just remains to add the stem and stern profiles. So I'll add 1 point, and then I need to adjust the section index here. So 23 was the last one I added. I'm going to change it to 1, which is my very first station, which is going to be the stem. So just click on the points, and you'll notice the subsequent ones use the same station index as the last one I entered. That could be quite useful if I'm adding points on a buttock line, for instance. I can specify the offset and then continue on the same buttock, and the offset will stay the same. So just finish off the stem profile here, and you can see because these markers are all grouped together, the line connecting them. And I'm going to do the similar sort of thing in the stern. So there I need to click on my point and then adjust the section index. So there it needs to be 24 for my very last station grid that I defined, and now the subsequent markers are going to have that same station index as the one I just edited, and you can see the line there joining those markers, showing they're all connected together on the same station index. And just checking the keel here, you can see because the lines are a bit difficult to see in the body plan view, some of my points aren't quite low enough, so I'm just going to edit that bottom point so that it lies on the bottom of the keel, and I can double click and edit its height to the cursor height that I just remembered. So there we've got a group of markers. You can see they're all connected together with a bold marker at the bottom indicating they're all starting in the same order. So now I'm going to look at how I can generate markers from importing a digital lines plan, e.g. a DXF file. It's best if we've got the body plan and maybe a stem and stern profile. So here we have a body plan, and you'll notice it's actually just a flat drawing in 2D. So what I need to do is move each station to the correct longitudinal position just by selecting it and moving it. So this is what I've done here. This has got all the sections moved over to the starboard side and all put to their correct longitudinal position. So switching back to MAXSURF, I can go to Import Markers and select DXF and select that 3D section plan. I need to specify which direction is forward, starboard and up in the DXF file, and also the units in the DXF file. And these will be read in as polylines, and each point on the polyline will generate a marker. So you can see there I've got a set of markers. If I've got a more detailed DXF drawing here with more lines on it, so here I've got the water lines, the buttocks, as well as the stations, all in 3D, then I can actually bring that in as a background drawing rather than individual markers, and this can help quite a lot when doing the fitting. So back in MAXSURF, so instead of importing as markers and DXF, I just go to import DXF background, and this is one common background between all the windows because it's a full 3D drawing. And again, I need to select the axes and the units, and you can see here these yellow lines indicate the DXF background that I've loaded in, and as you can see it's a full 3D model, so this can really help when I'm trying to fit surfaces to the to that DXF plan, and you can toggle it on and off with the view and hide button. I'm now going to show you some example workflows of how to generate tri-mesh surface models. These might be from digitized markers as we've seen before, or just generally imported from some other system. So the first thing we want to do after we've imported some markers is to delete any duplicates. So the simplest way to do that is to select all the markers and go to the markers menu, delete duplicate markers, and then set some tolerance. So here I've set a tolerance of 15 millimeters. 36 markers were in that tolerance, so I'll delete those. The next thing we need to do is define groups of markers that lie on approximately the same longitudinal position. So the simplest way to do this is to generate the grid from the markers. So the markers are grouped by specifying the station index. If the index is 0, then they're ungrouped, but if we specify a number of markers to be on station 1, for example, then they'll be grouped, and when we link marker stations we can see the line of all those grouped markers selected together. So we can automatically generate the station locations and specify the index for each of the markers so it's on this correct station from the markers menu using the Generate Design Grid from Markers dialog. So at the moment we're going to focus on just generating stations. We're going to delete any existing stations, and the number of markers that are required to define a station is going to be at least 4. So that means I need at least 4 markers at roughly the same longitudinal position for it to be counted as a station. And you can see it's basically picked up all the markers that are on the same longitudinal position. It will also try and sort them in the correct order, and here we can see it's got them all done correctly, with starting at the center line going up to the deck edge. So now it's relatively easy just to generate my tri-mesh. I go to tri-mesh, generate from markers, and again there's a few options such as symmetry. I wanted a symmetrical tri-mesh because my markers only define half the hull. And so that is my tri-mesh, and I can render that as well. So there's half, and I can use that to do hydrostatics and analysis. So for example, here I've got my curve of areas, and you can see that's calculated from that tri-mesh. Now I'm going to load in the markers that I generated by digitizing the lines plan. So what I need to do if I want to define a tri-mesh though is to make sure none of the sections actually overlap. So here where I've defined the stem profile, I've got some overlapping points here which I need to get rid of. So I can do that just by selecting them. If I use the shift button, I can add to the selection and then just press the delete button. So now that stem profile doesn't overlap the other sections. In fact, the sections don't need to be planar, it's just the overlapping that's the problem. In fact, what I should do is leave that one because that forms part of that station, but I'll get rid of these. And then I'll move these markers onto this section index. If I click here, I can see the station index is 22. So I'll select these markers and make them all 22. Go to the body plan view, you can see the ordering is incorrect, so I can select all the markers on that station, and normally the auto reordering should work correctly. So if I do markers, sort markers within stations, that will sort those markers on that station. And you can see now they correctly go from the deck edge to the centre line of the keel. And I can do the same for this marker which I want to put onto that station. So this was station index 23. So I'll select that marker there, make that 23. And again I need to check, ensure the ordering is correct. And again, so that all looks correct now. So now I can go to the tri-mesh menu and generate a tri-mesh from those markers. So the markers only define half of the hull. I'm going to use a symmetry flag to make the tri-mesh symmetrical, and I've got a few options here for adjusting the triangles and also deleting any triangles that are entirely on the centre line. So there it's generated my tri-mesh, which looks quite good. So here I've got a slightly more complex hull shape defined by markers again, but it's essentially the same process. So what I'm going to do is select all the markers and delete any that are within 15 millimeters. The tolerance that you put in is entirely up to you. So I deleted 5 markers. The next thing I want to do is generate that longitudinal grid and sort the markers into longitudinal positions. So if I go to markers, generate grid from markers, and again I'm going to use those same settings, 15 millimeter tolerance and 4 markers to define a station. And now we can see that actually there's a few issues in the stern area. It's easier to see that if I go into the body plan view and just view the markers for a single station. If I step through those stations, you'll see here, for example, the ordering has not worked. And the reason for that is the ordering is done by, first of all, finding the 2 markers that are closest together and then matching the next closest pair. So it's basically a nearest neighbour type of search. But the problem is that these 2 points that are in opposite sides of the keel are actually closer than the adjacent one. So it's making a link here instead of going all the way around. So the way to sort that out is to basically select the markers with the shift key down in order that they should be. So it's much easier for us humans to determine the correct order. Just go all the way around, selecting all the points. And then if we go to the markers menu, we've got reorder selected markers, so that will reorder those markers in the order that I've selected them. And you can see now it goes correctly down that bilge keel, or down that keel, and back up the other side. So I've got to do that for a few different stations. Again, here it's got it a bit better, but it's not quite correct. That final one's okay. The other thing I need to do is look at the bow. If I turn on all the markers here, so these ones that define the end of the bulbous bow are actually connected to this last station, but I actually want them connected to the adjacent one, so that these points will be connected to these ones here. So if I just see which section index that is, that's 24. So if I select all of these instead of 28, make that 24, and you see they're connected to this one. So now I can just go to the body plan, step through all my markers and just check they all look fine. So they all look okay. So now I'm going to generate the tri-mesh. So if I go to the tri-mesh menu, generate from markers, and leave the default settings, but especially delete the centerline triangles, which will remove any in the bulbous bow area. So I can see that something a little bit strange has happened to here. So the algorithm attempts to identify similar points on consecutive stations and connects them first. So often these sort of problems can be due to several markers being very close together or something like that. And if I zoom right in here, you can see I've got this funny spurious extra point here that doesn't appear on the other stations near it. So if I delete that point, so that the tri-mesh won't automatically reform, I need to actually delete it and then recreate it. And you can see here now it's all working correctly. So there are a few tricks that we can do to deal with bulbous bows when generating a tri-mesh. What we can do is add extra points on the center line to define the front of the bulbous bow and make them join onto the section in front, or the group of markers that define the section in front. And then when we generate the tri-mesh, we want to delete triangles that lie entirely on the center line. So this is my original model, and notice there's no closure to the bulbous bow in the front. So if I generate a tri-mesh there, it's going to try and close these two points with the nearest one on the next section, which is this point up here, but really we want it to close along here. So if I delete that tri-mesh, so what I'm going to do is insert some marker points. I've already got their coordinates, so I'll just do it in the table. Otherwise you can digitize them. So I'll just paste in these new marker points that I've already generated. If I see the perspective view, you can see these additional points that I've just added, and they join up to the section that's just in front of the last one that has part of the bulbous bow on it. So now if I generate the tri-mesh with the same option of deleting the triangles that are on the center line, these points here can close onto these points here of the section in front, and then these triangles that would be formed here are deleted because they're entirely on the center line. So another useful trick for more complicated tri-mesh models can be to use several tri-meshes. And here I've got some markers that define a hull and some more markers here that define a rudder. And so as to be able to select which markers are displayed, I've linked them to two different surfaces, one here the rudder and one here the hull. The surfaces aren't really used for anything other than hiding different types of markers. So in the markers table you can see the surface that each marker is linked to. So the top ones all belong to the hull, and then these lower ones here belong to the rudder. So what I can do is to create the tri-mesh for the hull is just show that surface, and what will happen is the markers that are associated with the rudder will not be visible. So if I select all of those markers, I can then form a tri-mesh to the selected markers. So there I've got a tri-mesh for my hull. In a similar way I can just display the rudder and select those markers and then generate a tri-mesh just for the rudder. So now I've got two independent tri-meshes, one for the rudder and the other one for the hull. And I can either leave these surfaces in the model or delete them when I've finished. So to summarize the workflow for generating a tri-mesh from markers, first of all we need to define the markers, and maybe they come from a CAD system, data points or digitizing that we've done. We need to organize those markers, basically grouping them in sections, and by giving them the correct station index. We can use the generate grid from markers command to do that automatically, and then on each station we want to sort the markers in the correct order from the keel to the center line. And we can use the automatic tools for most cases, but sometimes we might need to modify that manually. If you get things that don't quite work as expected, check for spurious markers, and also check for markers that you expect to be on the center line but might be just a fraction of a millimeter away from the center line.
So that concludes the first part of this webinar. Thank you very much for listening. In part 2 of this webinar, we will look at creating NURBS surface models in MAXSURF using the same data as we have used to create the tri-mesh models. Are there any questions?